Hello everyone, Bob here from Test Equipment Chronicles with Bob. Today we're going to talk about one of the most overlooked systems on an engine, and honestly one of the most important, the PCV system, positive crankcase ventilation. Now this is one of those components that tends to disappear into the background. It's small and it's inexpensive, and it's usually hidden somewhere in the valve cover or intake area. Because of that, people rarely think about it. But over the decades, I've come to believe something. This little system has probably extended the life of more engines than almost any other emissions-related component ever installed on a vehicle. And I learned that lesson early. Back when I was working heavily with muscle cars, I had some serious iron. A 1969 Mustang Mach 1 with a 428 Cobra Jet, a 1970 GTX with a 440. Those were real engines. Big displacement, high compression, built around performance. Now back then the thinking was pretty simple. If it looked like an emissions device and people wanted to remove it, and one of the first systems people tried to eliminate was the PCV system. But I started noticing something. The engines that still had proper crankcase ventilation stayed cleaner inside it. The engines that lost it often paid a price later. So today we're going to slow down and really explain why. Slide 2, what PCV means first. Let's define the term. PCV stands for positive crankcase ventilation. That word positive matters. It means we're not just letting vapors escape randomly. We are actively moving gases out of the crankcase. Manifold vacuum pulls contaminated vapors out of the engine and routes them back into the intake system, where they are burned during combustion. So if you want a simple picture, think of the PCV system as the vacuum cleaner of the crankcase. Fresh air comes in, contaminated gases go out. That continuous airflow keeps the inside of the engine cleaner, because engines are not sealed environments. They are constantly producing contamination. Slide 3, blow-by gases. Every piston engine produces blow-by. Even a new engine, even a well-built engine, during combustion, cylinder pressure rises dramatically. Some of that pressure leaks past the piston rings and enters the crankcase. That leakage is called blow-by gas. The amount changes with engine load, cylinder pressure, ring condition, and general engine wear. High compression engines done in older engines usually produce more blow-by. And that was something I paid attention to on performance engines. People were focused on horsepower. I was thinking about how to keep the engine alive. Slide 4, crankcase gas composition. Now what exactly is inside those gases? Blow-by contains unburned hydrocarbons, fuel vapors, carbon dioxide, carbon monoxide, water vapor, and nitrogen compounds. So those gases enter the crankcase, the same environment where the oil is trying to protect bearings, camshafts, rings, and cylinder walls. If those contaminants remain trapped inside the engine, they slowly degrade the oil. That's the problem the PCV system solves. Slide 5, chemistry inside the crankcase. Now here's where chemistry starts to matter. Inside the crankcase, several reactions can occur. Carbon dioxide mixing with moisture can form carbonic acid. Nitrogen oxides combining with moisture can contribute to nitric acid formation. Sulfur compounds can contribute to sulfuric acid contamination. Now we're not talking about laboratory beakers here, but we are talking about chemical reactions strong enough to matter over time. These acids attack the oil, deplete additive packages, and promote sludge formation. So the PCV system is not just an emissions device. It's actually a chemical damage control system for the engine. Slide 6. Moisture formation. Moisture is a big part of this story. Every combustion event produces water vapor. When the engine cools down, that vapor condenses inside the crankcase. Run the engine, shut it off, cool down, condensation forms. Repeat that cycle over and over, especially with short trips, and moisture begins to accumulate inside the oil. Years ago, I saw engines where you'd remove the oil cap and find that milky white residue, and people would immediately think head gasket failure, coolant contamination, something serious. But sometimes the real issue was much simpler. The engine just wasn't breathing properly, the PCV system wasn't doing its job, and moisture stayed trapped inside the engine. Slide 7, effects of acid contamination. Once contaminants remain in the oil long enough, oil degradation begins. Acids accelerate oil oxidation. Additive packages get consumed. Sludge begins to form. Varnish develops on internal components. Over time, bearings and metal surfaces lose protection. And here's the key point. This type of damage is usually slow. It doesn't cause immediate failure. Instead, it shortens the life of the engine gradually, 10,000 miles at a time. That's why the PCV system is so important. Slide 8, early crankcase ventilation, road draft tube before PCV systems. Engines use something called a road draft tube. Some younger technicians may never have seen one. The road draft tube simply vented crankcase gases downward. When the vehicle moved, airflow passing underneath the car created suction at the end of the tube. That airflow helped pull vapors out of the crankcase. It was simple. But it had serious limitations. It worked mainly when the vehicle was moving at idle. It did very little, and all those vapors were simply released into the atmosphere. So it wasn't very effective, and it wasn't very clean. Slide 9, closed crankcase ventilation. The PCV system solved those problems. Instead of venting gases to open air, the crankcase became a closed ventilation system. Fresh air enters the crankcase through a breather. Contaminated vapors exit through the PCV path. Those vapors are routed into the intake manifold and burned during combustion. That created two major improvements. Hydrocarbon emissions were reduced, and crankcase ventilation worked continuously. Even at idle. Slide 10, PCV system components. The system itself is fairly simple. You have a fresh air inlet, you have the PCV valve or calibrated orifice, you have hoses and passages, and you have a manifold vacuum source. Fresh air flows into the crankcase, moves through the engine, collects contamination, and exits through the PCV path. If any part of that airflow path becomes restricted, the entire system suffers. That's why diagnosis must always consider the whole system. Slide 11, PCV valve operation. The PCV valve is actually a clever device. Inside the valve is a spring-loaded plunger. At high vacuum, like idle, the valve restricts airflow. At lower vacuum, like during acceleration, the valve opens more, so the valve automatically adjusts ventilation flow based on engine load. That's why we often call it a calibrated vacuum leak. It allows a controlled amount of airflow into the intake system. Not too much, not too little. Correct calibration is important. Slide 12, PCV flow characteristics. PCV airflow is not insignificant. At idle, it can represent a noticeable portion of the engine's total airflow. If the valve flows too much, the mixture may become lean. If it flows too little, ventilation becomes inadequate. Years ago, people would do the classic test. Remove the PCV valve, shake it, hear it rattle, and declare it good. But that only proves the internal parts move. It does not confirm proper flow calibration. That's something technicians should always remember. Slide 13, blow-by pressure. Now let's talk about crankcase pressure. Blow-by gases continuously enter the crankcase. Without ventilation, pressure builds. Eventually the crankcase becomes positively pressurized. When that happens, the engine starts pushing oil outward, past seals, past gaskets, past weak sealing points. That's why engines with poor PCV operation often develop oil leaks. The seal didn't always fail. Sometimes the crankcase pressure simply overwhelmed it. Slide 14, crankcase pressure dynamics. When the PCV system is working correctly, the crankcase operates at slight negative pressure. Not much, just a small vacuum. That small vacuum helps prevent oil leaks, it helps remove moisture, and it helps evacuate contamination continuously. Years ago in the classroom, we sometimes measured crankcase pressure through the dipstick tube. A slight negative reading told us the ventilation system was working. A positive reading told us something needed investigation. Slide 15, anti-backfire protection. The PCV valve also serves another purpose. It helps protect the crankcase from backfire ignition. If an intake backfire occurs, you do not want that flame traveling into the crankcase because fuel vapors inside the crankcase could ignite. The PCV valve closes under reverse pressure. That helps prevent flame propagation into the engine's lower chamber. It's a small device, but it adds a layer of safety. Slide 16, PCV system. Failure modes, common failures include a stuck PCV valve, a plugged breather, collapsed hoses, or carbon buildup in the intake passage. Some engines also use internal separators or screens, and those can become restricted. I remember certain Ford engines where the screen below the PCV area would plug up. The valve itself might be fine, but airflow was still restricted. That's why technicians must diagnose the entire ventilation path. Slide 17, engine symptoms of PCV problems. When PCV systems fail, several symptoms can appear. Oil leaks, sludge formation, rough idle, lean mixture complaints, or signs of excessive blow-by. Sometimes the complaint is subtle. An oily smell, moisture under the oil cap, persistent gasket seepage. Over the years, I could often tell how well an engine was maintained simply by looking under the oil cap. Slide 18, crankcase pressure. Testing good diagnosis removes guesswork. Crankcase pressure can be measured directly. If the crankcase remains slightly negative, ventilation is working. If pressure becomes positive, either the PCV system is restricted or the engine has excessive blow-by. Older service tools like the snap-on blow-by meter helped quantify that airflow. Those tools made it easier to determine whether the problem was ventilation or internal engine wear. Slide 19, engine longevity and maintenance. The PCV system is inexpensive to maintain, but expensive to ignore. That has always been true. Years ago, a $2 part protected a several $100 engine rebuild. Today the numbers are larger, but the principle is exactly the same. One of my long-term examples was my 1970 CUDA 440. That engine had a lot of investment in it, and every oil change, the crankcase ventilation system received attention, because to me, that was cheap insurance. The PCV system was not the only reason that engine lasted, but it was absolutely part of the maintenance discipline. And that's the real takeaway here. Technicians often focus on dramatic failures, but engine longevity is often determined by small systems quietly doing their jobs for years. And the PCV system is one of the best examples of that principle. Closing well. I hope you enjoyed this discussion. It's a simple system, but a very important one. If you've been in the trade a long time, you've probably seen exactly what we talked about today. And if you're newer to the field, this is one of those systems worth understanding well. Small details matter. And in engine longevity, small details often make the difference. Thanks for spending some time with me today. This is Bob from Test Equipment Chronicles with Bob, and we'll see you in the next one.